I'd like to tell you a little bit about learning to learn for robotic control specifically. Maybe a good starting point is to look at the difference right now between how fast reinforcement learning agents learn versus how fast humans learn. And so this picture here is from a paper from Josh Tenenbaum's lab. What we see are in black dots is human players, horizontal axis is minutes played, vertical axis is score in the game. So what we see is that after about 50 minutes of play, humans are outperforming double DQN after it has played for 115 hours and often after it has played for 920 hours. So there's a pretty big gap here between what's possible with current RL and what humans are able to do. So the question is how we're going to bridge this kind of gap. I'd like to first take a little step back here and see, this is a slide adapted from Andrej Karpathy, and on the horizontal axis we have the quality of agents, in some sense, how much compute they're using, and the vertical axis is the kind of environment they'll be faced with. If we look at historically building controllers, initially we would just hard code them. It's just a simple environment. You can hard code a controller, one environment, and you're done. Then later over time we developed, as a community, value iteration, policy iteration, and so forth, we could allow us to solve bigger blocks worlds problems and maybe even some card pull problems, things like that. Moving on, we start using function approximators somewhat successfully. 2013, results on Atari, some universe games and so forth. And so we see here that as we use more and more compute, we let the data speak more and more for itself, and we can solve harder and harder problems. There's still this kind of zone of where we're just not getting to. For example, if we wanted to solve big multi-agent environments, or maybe real digital worlds, or maybe solve real-world problems, these methods are not really getting there for now, and maybe they won't get there. So what I'm going to advocate for is that to get there, to get past this possibility frontier, we actually need to somehow switch methods and do something that relies a lot more on data and compute and less on human ingenuity. And so what we'd have in the next generation of methods would be RL squared, let's say a meta-learning RL method, or even code generation, because ultimately often what's underneath what we do is code. And so I think to get to this real-world type challenges and try to solve them, we'll need these kinds of methods. The further we move to the right on this axis, the more compute we need. So this will require that we have more compute than we have today, but we're also projecting that in the future we'll have a lot more compute than we have today. For example, many companies are building dedicated machine learning compute that we could leverage to move to the right on this axis. Of course, there's a lot of meta-learning work already for optimization. Oriol summarized some of it for classification, for generative models. Here I want to focus on the control side of things. So one way to learn to control is reinforcement learning, where you learn from demonstrations, where you learn from your own trial and error. The other one is imitation learning, where you learn from demonstrations. So let's look at the reinforcement learning setting. We have an agent interacting with an environment, and hopefully it learns from that interaction with the environment to do better and better over time. Underneath, usually we have a reinforcement learning algorithm that updates a policy based on past interactions with the environment, and hopefully over time this policy becomes good. When you have a new environment, let's say first environment A, your algorithm will learn a policy for that environment. When you have a new environment, you can use the same code, the same reinforcement learning algorithm, but the policy will be relearned to now be tailored to environment B. Overall, what we see here is that the agent consists of two parts. There's a reinforcement learning algorithm and a policy. Could also be a Q function. Human experts develop the reinforcement learning algorithm and then let the algorithm fine-tune the policy. But even though we've spent at least 50 years now on designing reinforcement learning algorithms, we still don't have any algorithms that are as good as humans in terms of speed of learning. So maybe it's time to also let the other part be learned. Also learn the algorithm. So learn the entire agent rather than only learn the policy and design the algorithm by hand. So what would that look like? In meta-reinforcement learning, what we do is we look at learning the reinforcement learning algorithm. So what that means is that we somehow are hoping that we can develop an algorithm that's learned that's better than what we designed by hand. And the way that's going to play out likely is that this algorithm is learned by seeing a lot of interactions with many environments, and from that build up a prior over what the world tends to be like and code that inside the algorithm that now has a very strong prior, allowing it to learn more quickly. So it might interact with environment A, B, and so forth, and then somehow this meta-RL box spits out a fast RL agent that is good at solving new environments very, very quickly. How can we formalize this? How can we formalize learning to reinforcement learn? Actually, this formalism that was published almost identically out of OpenAI and Berkeley, and then DeepMind. These are the two papers at the bottom. Here's the formulation. We try to find an agent, which means some parameter vector theta that parameterizes the agent. That could be code, it could be a neural net, whatever you think is a good representation of your agent. We want that parameter vector theta to be such that if you sample an environment at random and then sample trajectories executed by that agent in the environment, that somehow that agent collects a lot of reward. Now keep in mind, this agent is not just a policy. It's allowed to adapt over time. So it's going to be dropped in an environment, let's say 2 times. Over those 2 episodes, hopefully has adapted, learned to do well in that environment, and then it gets moved to a new environment. And we're going to train it, hopefully, to be good at collecting reward in just capital K episodes in a single new environment it's never seen before. So we need to make some choices for what we put underneath. So here's our training objective. We need to choose what this agent is going to be. One thing we could put underneath is a RNN. The beauty of putting an RNN underneath is that it's very generic. It can encode any algorithm. It can encode prior about environments and so forth. If you look at it a little more deeply, the weights in the RNN would correspond to both the reinforcement learning algorithm and the prior over environments, somehow encoded in there. And then the different activations that the agent has over time would correspond to it adapting its policy as it's acting in a new environment. The meta training objective at the top can be optimized for with standard reinforcement learning. So what we do is we bootstrap off of standard reinforcement learning algorithms, let's say PPO, TRPO, A3C, and so forth, whatever is your favorite one, use that to optimize this objective, and the consequence would be a recurrent neural net that itself is an agent that has embedded in it reinforcement learning algorithms that are faster. Don't have to put an RNN underneath it necessarily. You can put something else, for example, a wavenet-like architecture, so dilated temporal convolutions, but then maybe with attention also so you can see more detail from the past than a wavenet would allow you to see. You can use the exact same objective, just a different architecture for the agent underneath that's being trained. Or you can do yet something else. You might say, well, we know gradient descent is pretty effective. Let's stick with gradient descent, and let's just see if we can pre-train an agent such that it's ready for fine-tuning when it's faced with a new environment. How would we set that up? This is called MAML. At test time, you're going to be fine-tuning. So at test time, you start with some pre-trained parameters. You get some new data, compute a gradient, do an update, get a fine-tuned parameter vector, and the hope is that this fine-tuned parameter vector is good at solving the task. How do you train for this? You can train this end-to-end. You can add training time. This is now meta-training time. You can set up a set of tasks. You try to find a parameter vector theta that is such that if you sample a task and then take a gradient step on the training data from that task, that you do well in the validation data of that task with just one gradient step. If you find a parameter vector theta that does this, then that's a really good pre-trained parameter vector that you can use to solve many tasks in the future. Once you have any of these architectures, it's interesting to start looking at how well can they solve problems that humans have already solved. For example, bandit problems, which are canonical reinforcement learning test problems, where you choose at any given time a bandit to play. That bandit has a probability of payoff, but you don't know ahead of time what the probability of payoff is for each of the bandits. And so you need to pull some bandit arms, figure out which one has higher probability of payoff, keep pulling that one. Humans, actually expert humans, have designed asymptotically optimal algorithms for this kind of problem. And so now we could look at, can our learned fast agent be as effective at solving a bandit problem as these human-designed algorithms? So the setting here is that after training, this agent gets dropped in front of a new set of bandits it's never faced before and needs to start exploring and exploiting in that new situation. Here's a table with results. The further we go down in the table, the bigger the problem setting is. What we see here is that all 3 approaches, some more than others, RL squared, MAML, and Snail, are able to be fairly competitive with human-designed asymptotically optimal algorithms to solve this kind of problem. So this is very interesting because it means that we can learn something that's as good or almost as good as the best you can hope for in this kind of environment. And all you need to do is run some learning. You don't need a lot of expertise into how to design bandit algorithms. Here's another example. Let's say we want an agent that is really good at adapting what it needs to do when controlling this cheetah robot. So different tasks here correspond to different speeds, or different. So here the goal is run forward as fast as possible. Here the goal is run backwards as fast as possible. Now the goal is to run at 0 speed, which is staying in place. And what we're watching here is the fully trained agent, meta-trained agent, being dropped in a new environment, which means a new target that it's supposed to achieve, and in the first episode, we're watching the first episode every time, adapts to what it's supposed to be doing here. We did something similar for Ant Robot. So what you see here again is the agent. You see the agent's very first episode controlling against that specific task after in the past having meta-trained on the Ant Robot and acquired a wide range of skills in the Ant Robot, and then now getting dropped into a new environment where a new target speed is requested. Here's another example, a scenario where you need vision and control. So here an agent gets to see monocular images in front of it, gets to steer 2 degrees to the left, 2 degrees to the right, or go straight. It's supposed to navigate this maze and go to the target destination. But it doesn't have the map of the maze. It only has the monocular images. And so what we see here in action is this agent reliably navigating this maze. It doesn't know the map, so it's actually doing something quite reasonable. It's exploring this maze very effectively. It's never been in this maze before, but it's trained to become good at navigating mazes it's never been in before, reliably explores this maze, and exhaustively explores what's possible without wasting time on anything, and finds its way to the other side again. Takes an unlucky turn one more time, and then finds the goal location, runs right to it. So it learned a whole memory system to navigate mazes and low-level control as well as low-level vision processing. If you want to do something that is extended actions over time, you could, for example, train an architecture like this, where you have a master policy and then sub-policies phi 1, phi 2, phi 3, which execute at the full control rate. The master policy switches between them. And then you can train this in the meta-learning setting. This is the original RL squared type meta-learning setting. Here what we then do is we say, let's find sub-policies parameterized by phi, such that if a master policy is being trained by a reinforcement learning algorithm, and that master policy is initialized randomly with the parameter vector theta 0, and it's randomly dropped in an environment M and gets to experience capital K trajectories, those sub-policies should be really good at allowing this agent to succeed, to train on top of those sub-policies. What you see then is that, for example, for the moving bandit problem, it learns sub-policies to go to specific types of bandits. For an ant that's supposed to navigate mazes, it learns different low-level gates moving diagonally down, sideways, or diagonally up. And it discovers those not by us telling that we want these gates, but by that those are the gates that allow a master policy on top of this to maximally quickly adapt to new environments. Here are a few references that you can look at later. We can't just reinforcement learn, we can also learn to imitate. Imitation learning has been quite successful in many ways, but typically this canonical paradigm is used where you imitation learn for each task separately. So maybe assembling a chair, then assembling a table, and so forth. Meta-learning would be the notion where you actually see a lot of demonstrations and then learn something that can, in the future, imitate from one example. So you give one example of a new task, it immediately learns how to do it. The way you can set this up is you would train a one-shot imitator, a big neural net in this case, by showing it 2 demonstrations of the same task. And it's supposed to, by looking at the current frame in demo 2, predict what the right torque is to apply for this robot by parsing demo 1. If it can do that reliably, it means that it can, from that one demonstration, demo 1, predict what needs to happen in the new situation. So this is just a supervised learning problem, the way this is set up, to train a one-shot imitator. We looked at this for block stacking. I'll skip over this video. We looked at this for robot execution, so let's watch that one. So here on the left is the demonstration. Robot is placing the object into the white ball, and just from this raw stream of pixels and the torque values applied to the robot, one example, it can learn to do the right thing in the new situation on the right. If the demonstration puts the object onto the yellow placemat, it'll do something similar in the learned behavior. Again, just from one demonstration, going from raw pixels to motor commands. Okay, so what are some current directions? I think the examples I've shown to you are promising, but are still solving relatively simple problems compared to the real-world problems you really want to solve. And a lot more work is needed to figure out how to do that. Some of the work might be algorithmic. I think a lot of it will also be representationally. Different neural architectures, maybe that have more memory in them than the ones I've shown here. Maybe code that is standard programming type representations, because those generalize really well, typically, to new situations. Another big challenge ahead is to actually move from the standard meta-learning setting I've shown you, where you get dropped in a new environment and need to do well, and then it's over, to something where you continuously are faced with a changing environment. This would be the lifelong learning setting. This could be because the environment is non-stationary, or it could be because you have competition. If you have competition, and the competitors are constantly adapting, you need to adapt to what they are doing, or you're going to fall behind and constantly be losing. So for example, what we're watching here, the red robot, the four-legged one, is a meta-learner, and so is better at adapting to its opponent. And while it starts out as a weaker sumo wrestler, over time it actually starts consistently beating the green six-legged robot, because that one is just using regular reinforcement learning and hence doesn't adapt nearly as quickly to changes in its environment. Thank you.
May I ask a question that I'm not sure that I understand why the meta-learning is very important for the reinforcement learning problem. Why it can improve the performance since it's also based on the SGD. I'm not sure, but I guess one of the reasons that SGD may not enough to search in the very highly non-convex space. So the meta-learning can help the SGD for that. Am I right?
So I think there's a few parts to your question. So one part of the question is, why would meta-learning help for reinforcement learning?
Yeah.
And so I think that's actually quite similar to why it would help for some of the other problems. And the reason it will help in reinforcement learning is because if you have a strong prior over what the world is like, you can learn more quickly. So to see this in the extreme, let's imagine you did model-based reinforcement learning. And in model-based reinforcement learning, all you need to do is figure out the model of the world that you're acting in and what the reward function is. Once you have that, and if you have a really good planner, you're done. So then it's just a matter of identifying what world you're in. In that specific scenario, which is the easiest one to think about, what happens is, if you have a really good prior over what the world can be like, from a small amount of data, you might be able to identify what the world really is like that you're faced with. Whereas if you don't have a good prior, it's going to be very hard to identify exactly what the world is like, and it's going to take a lot more data collection on the spot to get that kind of expertise.
So do you mean that the meta-learner help to model something about the environment so that can be learned quickly?
Yeah, the best way to think of it is that the meta-learner models what environments can be like. So there's many types of environments you could be faced with, and the meta-learner models a strong prior over what the environments are that you might face in the future. And then at meta-testing time, it'll essentially exploit that prior to adapt much more quickly than a system that does not have this kind of prior.
Okay, thank you very much.
Okay, thank you.